Most of us assume space and time are fixed and the world is just sitting there. The same for everyone. Oh, we haven't got much light there, have we? Sorry. See if I can get a bit more light. In fact, yeah, I'll turn the main light on. If it works. There you go. Right. But that starts to break down when you look closer. Move fast enough or get close to something massive and space shrinks, time slows, and reality itself bends. So before we go further, if space and time can change, what exactly is real? This is part 6 in chapter 1, the hard science, part 6 in the video series. And we are on now section 3, relativity, space, time, length, mass and dilation. So, where are we with physics right now? Over the last century, we've built 2 stunning theories, elegant, accurate and experimentally proven over and over again. First is Einstein's general relativity, which flipped our whole sense of reality. The word relativity gets thrown about like it's some mysterious code, but the basics are actually pretty straightforward once you peel away the maths. Einstein's big insight was that space and time aren't separate things. They're stitched together into a single fabric called spacetime. Imagine a dance floor that bends and twists depending on who's stamping around on it. That's the universe. Let's start with special relativity. Picture 2 people, one standing on a platform, the other on a train flashing past at ridiculous speed. Both think they're at rest in their own frame of reference. Einstein's genius was realizing that neither perspective is truer than the other. The laws of physics work the same for both. But to keep this consistent, something has to give, and that something is how we experience length, mass and time. The theory also has to set the speed of light in a vacuum as a constant, irrespective of the frame of reference, and that in itself is very strange. It is important to point out here that these effects are utterly unnoticeable at speeds we humans usually encounter, hence we don't notice them. They only really come into effect if the train were travelling at close to the speed of light, which is approximately 187,000 miles per second. Here's the weird part. As you move faster and faster, again close to the speed of light, lengths in the direction you're moving get shorter, infinitely small if you could reach the speed of light. This isn't an optical illusion, it's built into the structure of space-time. Mass also changes. From the perspective of the person standing still, the faster you go, the heavier you become, edging towards infinite mass at light speed. That's why nothing with mass can ever actually hit the speed of light. You need infinite energy to push it that far. And then there's time dilation. The faster you move, the slower your clock runs, compared to someone who's standing still. From your point of view, inside the speeding train, everything feels normal. But when you look back, less time has passed for you than for your mate left behind. That's special relativity in a nutshell. It governs situations where gravity isn't muddying the water. But what about the big stuff, where stars and planets are bending the stage we're dancing on? That's where general relativity comes in. General relativity takes the same core idea, space-time as the fabric, and shows how mass and energy warp it. A planet, a star, a galaxy, all of them create dents and curves in space-time. And things moving through that curved space-time follow the bends. We call that gravity. But Einstein flipped the script. Instead of some invisible force pulling objects together, which is what Newton told us, it's just things following the natural paths carved out in the fabric of reality. The Earth orbits the Sun because the Sun bends space-time around it, and the Earth is simply rolling along the curve. The consequences are everywhere. Time passes at different rates depending on the strength of the gravitational field you're in. Clocks on satellites tick slightly faster than clocks on Earth's surface, because gravity is weaker up there. GPS wouldn't work unless we accounted for this. Even light bends when it passes close to a massive object like a star, It's how we can see distant galaxies magnified through what's called gravitational lensing. Put it all together, and relativity changes how we see reality. Time isn't fixed, mass isn't fixed, length isn't fixed. They all depend on your frame of reference. At everyday speeds and scales, it doesn't matter really. But at the edges, near light speed, near black holes, it rewrites the rules completely. So next time someone tells you time is absolute, or space is just an empty stage, you can smile and shake your head. Einstein showed us otherwise. Reality is more flexible, more dynamic and stranger than common sense ever imagined. Relativity indicates that the objective reality is far weirder than our intuition indicates. But what comes next takes this to an extreme. So, what this section is really doing is showing that space and time, mass and length are not fixed but depend on how and where you observe them. And if that's true, then there is no single shared version of reality that everyone agrees on. Because the real problem may not be how the universe behaves, but how observation itself shapes what we call reality. So, if this isn't what we thought, what are we actually standing inside of? Next up, we go to chapter 1, still in chapter 1, the hard sciences, and we're on section 4, quantum mechanics, the strangeness of the small. And if you thought relativity was weird, here we go.